Have you ever really thought about what happens inside your computer when you click something? I mean, we all call the CPU the brain, but what does that actually mean? Well, today, we're going to pull back the curtain. We're going to follow a single piece of data on its incredibly fast journey right through the heart of the processor.
So here's the game plan. We'll start big picture with a whole computer on a tiny chip. Then we'll zoom right into the CPU's inner circle. From there, we'll actually follow an instruction, step by step, and meet the special components called registers that make it all work. And finally, we'll see how this whole dance is designed for one thing: pure, mind-bending speed.
Okay, first things first. Before we can understand the brain, we kind of have to understand the body it lives in. So let's talk about what a computer on a chip really is. What you're looking at here is a microcontroller. And yeah, it's basically a whole computer squished onto one piece of silicon. You've got the three main players: the CPU, that's our brain. You've got memory, think of that as its library and its short-term scratch pad. And you have the I/O unit, which is how it talks to, the rest of the world. And that line connecting them all? That's the system bus. It's the superhighway that all the information travels on. All right, now for the main event. Let's leave that system highway behind and go right inside the brain itself, the central processing unit. So, it turns out the CPU isn't just one single thing. It's more like a highly specialized team. You've got the control unit, who's basically the director, reading the script and telling everyone else what to do. Then there's the ALU, the arithmetic logic unit. That's the math whiz, the master calculator. And then you have the registers. And this is our focus today. These are the CPU's personal, ultra-fast workspace. This is where the magic really happens.
And when I say fast, I mean it's hard to even describe how fast. A register is the fastest possible place to store data in a computer, period. It's not just a little bit faster than your main RAM. We're talking a completely different universe of speed. Getting data from a register can be over 100 times faster than going all the way out to main memory. It's instantaneous.
This analogy just nails it. Imagine the CPU is a master chef. The ingredients it's actively chopping, mixing, and cooking are right there on the countertop, within arm's reach. Those are the registers. Now the RAM, that's the pantry down the hall. It holds all the other ingredients, sure, but the chef has to stop everything, walk to the pantry, find what they need, and walk back. That little walk, in computer time, that's an eternity.
So, we've met the players, now let's watch the game. We are going to follow one simple command, an add instruction, and see exactly how the data flows between the memory pantry and that register countertop. And here's our starting line. Over on the left, you see our program and data just sitting there in memory. On the right, our CPU's registers are ready to go. Now pay close attention to the program counter, the PC. See how it's pointing to memory address 0x200? It's basically a little bookmark telling the CPU, hey, the next thing you need to do is right here. And we're off! Step 1 is the fetch. The CPU looks at the program counter, uses that address to grab the instruction, that 0E02 value, and immediately loads it into the instruction register, or IR. The IR's only job is to hold on to the command we're working on right now. But look, the program counter has already jumped ahead to 0x202. It doesn't wait around. It's already getting ready for the next cycle. Okay, next up, the control unit looks at the instruction in the IR and decodes it. It's like reading a recipe. This one says, go get a piece of data. So the CPU executes. It grabs the value 02 from memory and puts it right into the accumulator register, which we'll call A. The accumulator is a special register, kind of like a mixing bowl for math. Our first ingredient is now on the countertop. And now for the finale. The next instruction is fetched, and this time it tells the ALU, the math whiz, to get to work. It takes our second number, 05, straight from memory, adds it to the 02 that's already sitting in our accumulator, and boom, the result, 07, is stored back into a spot in memory. And that's it. From memory to a register, through the math unit, and back out again. The life of that one little instruction is complete. So we just saw them do their thing in that little data dance. Let's take a quick moment to properly introduce the all-star team of registers that made it all possible.
So, let's recap the core team. The program counter is the what's next register. The instruction register is the what are we doing right now register. The accumulator is our calculation scratch pad. And working kind of behind the scenes was the memory address register, or MAR, which basically acted like a temporary GPS coordinate, telling the CPU exactly where to look in memory. Each one has a very specific and very vital job.
So why does any of this matter? Why obsess over this microscopic step-by-step process? Because making this little dance faster, Well, that's the single biggest obsession in all of computer engineering. It is the quest for speed.
You know, everything we just watched, it all boils down to this fundamental three-step loop. Fetch, decode, execute. This cycle is the literal heartbeat of every single digital device you own, from your phone to your car, and it happens over and over and over again, billions of times every second.
So, how do you make that heartbeat faster? Simple. You don't wait for one beat to finish before starting the next. This trick is called pipelining. Just look at this diagram. Instead of doing one task at a time, the CPU works like a factory assembly line. While one instruction is being executed, the next one is already being decoded, and the one after that is being fetched. It's a brilliant way to overlap all the work and just cram more stuff through.
And this whole quest for speed actually led to two big competing ideas. On one side, you have RISC, that's Reduced Instruction Set Computer. The idea here is to use tons of simple, super fast instructions that are just perfect for that assembly line pipelining. On the other side is CISC, Complex Instruction Set Computer. This philosophy uses more powerful instructions that do more in a single step, but they're a bit clunkier and harder to pipeline. It's the classic trade-off, right? Do you use 100 tiny, fast tools or one big, powerful but slower machine?
So think about that. The tiny journey we just followed, from memory to register and back, happens on a scale and at a speed that is almost impossible for our brains to comprehend. And engineers are working around the clock, relentlessly pushing to make it even faster. Which leaves us with a pretty cool question. As this fundamental heartbeat of all computing continues to accelerate, what will that make possible next?